Hi, my name is Pavel Skriptsov and I would like to share some example of using particle filter. In the applications that we develop, sometimes we use particle filter, and this particular simulation is our playground where we study various aspects of particle filter algorithm behavior. And in this particular simulation, it's easy to see how and understand how particle filter works. And if you just read about how particle filter algorithms is constructed and you need to get some additional example, this is for you. So in this situation, that we model, we try to predict the position of the falling object. Let's say that's an object that enters our atmosphere, and in the initial time step, we don't know where this object is located, which is represented by white dots. You see that each dot is drawn from the initial distribution, which is wide, and we don't know where the object is, so the mean of the distribution does not coincide with the true object position. For some selected particles, the velocity vectors are also displayed, which shows our initial uncertainty about the object velocity and even the direction of the velocity. Now we also have three measurement stations here, distance measurement stations, and their measurements are schematically displayed as the circles, as they report the distance to the object to the system. So now to make things a little more complex, we made it so that not stations work all the time. So they have some update rate, and the system doesn't have information from all the sources all the time. So the thing which doesn't work is shown as gray. So as you know from the particle filter algorithm, the first step is usage of the dynamics object of the system, and in our case the dynamics model of the object is adding speed to the current position provided delta of the time passed. And before we did any measurement, we can see that basically this means that our initial cloud of objects extends. Now, as we done the first measurement, you can see that particles changed their color, and some of these became dark gray and some of them became white, which represents how well this hypothesis matches to the measurements that we done at this step. And in this particular step we've done two measurements, and so particles which are close to these circles are lighter than those which far from it. After resample, that is the process of killing particles with low probabilities and increasing the number of particles in the areas of the phase space with high probability. We see that our mean, which is displayed by this green circle, jumped closer to the actual position of the object. So now we go on, and in this particular step we see that two measurement units didn't work. We only had one measurement from the one of the stations, and it's easy to see that the distribution of weights now almost repeat the form of the measurement surface. In this case, this is circle, and its width is determined by the measurement noise. In our case, measurement noise is described with the width of the circle, which displays basically 1 sigma of the Gaussian distribution. So now as we continue to run the particle filter algorithm, we see that even if we have lack of measurements, and the dynamics model of the object allows us to approximately track the position of the object, even in situations where we mathematically have not enough information to make the actual solution. So now, as we have a secondary measurement available, we see that the distribution has collapsed towards the true mean, true position of the object, and the location of the mean now is much better close to the actual position of the object. So now we can continue running the simulation and see how particle filter algorithm tracks our object. So as you see, for many steps we have a lack of measurement information that would allow us to measure the location of the object, and you see that the particles spread around the measurement surface until we get new measurement that allows us to narrow down the distribution and keep our mean close to the position of the true object. So in this model we see that particle filter allows us to make data fusion, that is, to integrate information from multiple measurements into the single estimation of object position. Also, I must note that particle filter allows us to solve inverse problem, is that because nowhere in algorithm of particle filter we have code for solving nonlinear equation systems. That is, we don't have to think how we could cross this measurement with that measurement and receive our location. Instead of that, we only describe what would certain measurement show us, provided that we know the location and the velocity of the object, which is much easier to do than to solve the inverse problem, where we would have to explicitly write system of equations to cross several measurements and form the actual position from it. Now also see in this particular example you can see that solving the system of nonlinear equation could result in multiple solutions, and it would be another problem of selecting a proper solution, and in this case it's done automatically because we have a dynamics system which helps us to understand that the object with modeled velocities couldn't instantly move to this location. And in some cases the situation is even worse than this, and the solution of the nonlinear equations would result in surfaces, in subspaces of solutions, not individual dots. And we would have to live with that, and that is done with the particle filter automatically. It just spreads the particles along the axis of uncertainties, and as soon as a new measurement comes that allows us to diminish this uncertainty, the particles distribution reflect that measurement and collapses towards the true location of the object. The particle filter is quite easy algorithm to implement, and it results in object-oriented code where each measurement can be represented as an individual object. So, for example, now I turn off one of the distance measurement units and turn on the bearing sensor, which would provide once upon a time the angle to the object. So now, returning to the situation, to the initial situation, we see that the bearing allows us as well to narrow down the distribution of particles towards the true location of the object, and helps to track our object. Well, I hope you like this particle filter example, and I can also tell you that we don't just get estimation of the position, we also get uncertainty to which extent we know the position of the object, and in some cases this can be a multiple mode distribution, not always Gaussian, and maybe in some later videos I'll show how this can be used in real applications where we would like to keep these uncertainties like multiple modes in object location to be able to later resolve them with upcoming measurements. Thank you very much. Goodbye.